The training program you're about to view is one of our classics. Even though it may have been taped years ago, it still shows expert linemen providing professional work practices. Make it a point to always follow the established work practices of your company to help in your safety and the safety of your coworkers.
This is Spanner's Tygard line tie. This is Spanner's Tygard line tie. Its versatility and efficiency in meeting your construction requirements is best illustrated by an actual field test report involving Tygard line ties. The test sequences you're about to see were supplied through the courtesy of Florida Power Corporation, St. Petersburg. These tests were performed as a result of a car hitting a pole in a 795 MCM AAC feed line using hand ties over line guards. It caused a cascading failure of 27 consecutive post-type insulators. As a result of this experience, it was decided to test various post insulators and ties to evaluate present construction standards and materials. Test site was St. Petersburg, Florida. On a dark and rainy day, 9 consecutive tests were performed with a variety of post insulators and ties. The test site was nearby the Florida Power Corporation's Bartow generating plant. The test setup included a quick release device on pole 1, 40-foot poles, 795 AAC conductors, 7/16-inch guy strand, 1/0 triple AC neutral, 300-foot pole spacing, 30-inch conductor spacing, and 36-inch bottom phase to neutral spacing. Test action was filmed only at pole number 2. Conductor tension, insulators, and tying methods used will be stated preceding each live sequence of the following tests. Test 1 is in 2 parts, transverse and longitudinal. Tested were 20 kV F-neck insulators and Tygard line ties. Conductor tension, 2,600 pounds. In the transverse test, the third pole was storm guyed about 6 feet above ground. A 1,250-pound horizontal force was applied just above the neutral and released. Action viewed at pole number 2 was minor. As was expected, very little happened. When the ground line was released, pole number 3 whipped sluggishly. There was little movement and no damage at poles 2 and 4. In the longitudinal test, phase C in the red was released. The Tygard line tie held. Results of this test showed that the insulator bolts bent at poles 2 and 3. Tygard line ties held. There was no effect at pole 4. In test 2, a 15 kV F-neck insulator was used. The conductor was again tied with Tygard line ties. Transverse load tests were discontinued because it was felt results would be identical to test 1. Test number 2 was a longitudinal test. The action seen at pole 2 was much the same as before. Results were practically the same as test 1. Insulator bolts bent on poles 2 and 3. Tygard line ties held. Again, no damage at pole 4. Test 3 was different. 20 kV C-neck insulators were used. Conductor was secured with number 4 aluminum tie wire over line guards. Action at pole 2 immediately showed a failure. With a broken tie, the conductor ran over the insulator. The line continued running until it was nearly on the ground between poles 2 and 3. Here's what happened. The shock was too great for the tie and it broke. So the failure went on to pole 3, where the conductor slipped. It also slipped slightly at pole 4. A cascading failure was almost produced. In test 4, clamp top insulators were used with line guards on the conductor. Action seen at pole 2 indicated that virtually nothing happened in this test. When the conductor was released, the insulator held, but the bolt bent. The same thing happened at pole 3. There was no effect at pole 4. The only setup difference in test 5 was the gain base on the insulator. All other factors were the same as in the preceding test. This time, as you can see, the insulator failed at pole 2. Here are the results. After the release, the gain base insulator broke at its base. At pole 3, the insulator bolt bent 45 degrees. It also bent at pole 4. Nothing happened at the 5th pole. In test 6, tension rating was increased to 3,700 pounds. 20 kV clamp top insulators were again used. Line guards were also used. Again, failure was obvious at pole 2. This time, the failure continued into a cascade. Here, the insulator at pole 2 failed. The impact that hit the insulator at pole 3 forced open the keeper. The insulator at pole 4 also snapped. At pole 5, Tygard line ties were used, and the resulting cascade was stopped. Only the bolt bent. In test 7, 20 kV C-neck insulators and hand ties over line guards were again used. Tension was 3,700 pounds. As in test 3, a failure was caused when the tie wire broke. The results showed a complete failure at the second pole as the tie wire broke. The insulator bolt bent at pole 3, and the conductor slipped. The conductor also slipped at pole 4 with no other effects. Test 8 was performed with 15 kV F-neck insulators. Tygard line ties were put to the test with a 3,700-pound load. If the tie was destined to fail, it would have with the second shock. Even at the higher tension rating, Tygard line ties held fast. The bolts bent at poles 2 and 3 with no other effect. Pole 4 had no damage. Test 9 was set up to see what would happen if all 4 lines failed at once. Tying was with Tygard line ties. This test was made by dropping all 3 phases and the neutral at one time. Release was made before the camera started. Here's what happened at pole 2. All that happened was pole number 2 shifted and the insulator bolts bent. The Tygard line ties used held throughout. Florida Power made these observations. Bending of mounting bolt on distribution class insulators acts as a shock absorber. Stiff-mounted gain-base insulators do not dampen shock and are prone to failure. Fanner Tygard line ties are far superior to hand ties over line guards. Spring-loaded helical components in Tygard line tie loop deflect and absorb energy. Tygard line ties help limit excess load on post insulators. 2.5-inch square washers bend and pull into poles. 3-inch curved washers do not bend nor pull into poles. The test conclusion was that standard construction with distribution post insulators mounted on slab gain poles, 5/8-inch bolts, 3-inch curved washers, and formed ties will withstand forces under broken conductor conditions. Let's take a close look at Fanner Tygard line ties and how easy they are to apply. Here's how a Tygard line tie is hand installed. Notice how easily a Tygard line tie goes on. It takes longer to explain the installation than it does to actually do it. No pads, no fillers. The most reliable line tie made. There are Tygard line ties for almost every size conductor or neutral, for most insulator or shiv applications. Each design is color-coded to show conductor and insulator neck size. Splitting the ends on larger sizes makes the final end snapping much easier. With a snap at the end, it's on. Removal for reuse or repositioning is also quite easy. A screwdriver helps get the wire end started. Now you simply unwrap the leg. And here's how it's done with Hotline tools. When the line is hot, installation is virtually the same as by hand, except it takes a little longer with hot sticks and pigtails. Because of the pre-shaping of the tie and the pre-sized helical legs, installation is really quite simple. The installation sequence shown here is actual. The time involved to install the tie is real. The result is a permanent tie that won't fail. Fanner's Tygard line tie simplifies replacement of broken insulators. Removal of one leg is all that's required to lift off the conductor. You've just seen Fanner's field-tested, field-approved Tygard line ties. Dependable and economical for your overhead construction. Specify Fanner Tygard line ties. Results of these tests have been published in book form and are available from Fanner.